By area moment method, compute the slopes and deflection at C. IABC is I while ILCF is 1.5 I and E is constant. So to my subscribers and to those who are new in my channel, to keep me going, to keep me do, make lecture videos and sample video problems, please share my videos because to your friends and to your friends' friends, and help me promote my channel because that keeps me energized and do lecture videos and sample problem videos that are very tiring, especially if I draw the figure in more details to keep my audience understand my presentation. So help me promote my channel. If you want me to do more lecture videos and sample problems in any engineering subjects, especially civil engineering. So to start with, let's compute for reaction at B. This time, let's select C as our moment center so that you will have an example where I choose the hinge as the moment center. In our preceding problems, we selected two different points, not the hinge, but this time let's select C as the moment center. So moment about C equals 0 considering ABC, so BY times 5 minus 25 times 7 equals 0. So BY is equal to 35 kilonewtons upward, so let's apply it. So therefore, the reaction at C just to the left should be 10 kilonewtons downward. Then by action-reaction, 10 kilonewtons upward at C. Then let's solve for reaction at F. So summation moment D equals 0, counterclockwise positives. So moment about D equals 0 equals RE rather times 8. Then minus 10 times 6. Then minus 32 times 15. So the distance of the centroid from the right is 7.5. So therefore, to make this 8 plus 1, 9, so this should be 1.5. So minus 32 times 15 times 1.5. So reaction at D can now be computed. It is equal to 97.5 kilonewtons. So let's now prepare the moment diagram by parts. So remember, we select C as our moment center. So 25 times 7, the moment of inertia is just I, so there's no need to divide by 1.5. 25 times 7 is 175 over EI. Then this is 25 times 2, so 50 over EI. Then 35 times 5 is 175 over EI. Then sorry, let's select D as the moment center, rather, not C. So 10 times 6 is 60 divided by 1.5, so that's only 40 over EI. Then due to this loading, 32 times 6 times 3, second degree, 32 kilonewton per meter times 6 times 3 divided by 1.5. So that's 384 over EI. Then for this loading here, we first replace this loading in the overhang by 32 times 1. So there's concentrated load, which is 32 kilonewtons. Then the moment of second degree curve is 32 kilonewton per meter times 1 times 0.5. So this is a moment of 16 kilonewton meter, which is clockwise. And let's plot that from F to E. So this is second degree, and we have 16 kilonewton per meter divided by 1.5, so 32 over 3. So 32 times 1 times 0.5 is supposedly 16. Then divide by 1.5, that's why you have 32 over 3 EI. Then let's transmit it to D. Sorry, we selected D as moment center. That's why I did not solve for reaction at D. Then moment due to the 32 kilonewton load, 32 times 8 divided by 1.5. That's the height. The height is 512 over 3 EI. Then due to this uniform load, this is not yet included. 32 times 8 times 4 divided by 1.5. It is a second degree curve. Again, 32 times 8 times 4 divided by 1.5. The height is equal to 2048 over 3 EI. Since we need the slopes and deflection at C, we need the tangent at D, then transmit it there so that we can analyze. So therefore, we should compute division of E relative to the tangent at D. And this is the moment due to the reaction 97.5 times 8 divided by 1.5 is 520 over EI. So this is the complete moment diagram by parts. There are so many areas. But if we consider only portion of the beam, then we can reduce the areas as well as the location of the centroids. So EI division of E relative to the tangent at D is first this positive area, 0.5 of 8 times 520 times moment arm 2/3 of 8, so 16/3, 0.5 times 8 times 520 times 16/3, then minus 8 times 32 over 3 times 4, then minus 0.5 times 8 times 512 over 3 times 2/3 of 8, so 16/3 again. We consider only areas between D and E. Then minus 1/3 of 8 times 2048 over 3. So this distance is 8 over 4, so 2. Its distance from the right is 6. That's why you have 6 there. So using your calculator, division of E relative to the tangent at D is equal to negative 34,304 over 9 EI. So since it is negative, it means that that point E is below the reference tangent at D, as shown in the figure. So this is division of E relative to the tangent at D. And therefore, we can compute theta D, which is sloping up to the right, so it is positive. Theta D, the angle that this tangent at D makes with the horizontal, this is also theta D. So theta D is positive division of E relative to D, which is 34304 over 9 divided by 8. So theta D is equal to 4288 over 9 EI. Then having known theta D, let's transmit it here. Let's compute division of C right with respect to the reference tangent at D. So EI division of C right relative to D is 0.5 of 6 times 4 over EI. Then moment arm from C right is 2/3 of 6, so that's why you have 4. So this distance is 6 over 4, 1.5. So the distance of the centroid from the left, from C right, is 4.5. So minus 1/3, this area here, times 6 times 384 times 4.5. Where 4.5 is 6 minus 1.5, and 1.5 is 6 over 4. This is 6 over 4. So that's 4.5. So division of C right with this relative to D can now be computed, and it is negative 2976 over EI. Because it is negative, again, C the deflected shape or the point C on the elastic curve is below this reference tangent at D. So it should be below this one. And this is deviation of C right relative to the tangent at D, negative. So it's below. We now draw the elastic curve. By the way, this is 6 times theta D. And this is deviation of C relative to D. The vertical distance from original point on the beam to this point here is the deflection at C, which is negative. And this is negative of absolute value of quantity 6 theta D plus absolute value of deviation of C right relative to D. So EI theta C right D is just the area. So we remove the moment arm, 0.5 of 6 times 40 minus 1/3 of 6 times 384. So theta C right D is equal to negative 648 over EI. So negative means from the tangent at C right to the tangent at D, it is again clockwise. So it is above this tangent at D as shown in the figure. So this is the tangent at C right, then from tangent at C right to tangent at D clockwise because that's negative. So this is theta C right D. And the angle that the tangent at D makes with the horizontal is theta D. The angle that the tangent at C right to the horizontal is theta C right. So obviously from the figure, theta C right is positive because it is inclined up to the right, and it is the absolute value of theta C right D plus absolute value of theta D. So we can now compute theta C right, which is this. So theta C right again is theta C right D plus absolute value of theta C right D. It is positive, inclined up to the right, plus theta D. So theta C right is equal to absolute value of theta C right D, which is negative 648 over EI, plus theta D, which is 4288 over 9. In decimal, theta C right is equal to 1124.444 over EI. Delta C, on the other hand, which is this vertical distance negative, is negative of absolute value 6 times theta D plus absolute value of deviation of C right relative to D, which is negative 2976, and this is theta D. So computing using your calculator, delta C is negative 5834.667 over EI. Then we need to compute deviation of B relative to the tangent at C left because delta C has been found. If we know the deviation of B relative to the tangent at C left, then we can compute the total vertical distance, and because there is horizontal distance 5, then we can compute the slope at C left, which is the only remaining requirement in this problem. So EI deviation of B relative to C left is equal to moment of areas between B and C left with respect to B. So 0.5 of 5 times 175. Then the distance of centroid from B is 2/3 of 5, so 10/3. Then there is trapezoidal area here. Let's divide it into two triangles. For the smaller triangle, minus 0.5 of 5 times 50 times 5/3. The moment arm is 5/3 for the smaller triangle. For the bigger triangle, it is 2/3 of 5, so 10/3. So minus 0.5 of 5 times 175 times 10/3. So using the calculator, deviation of B relative to C left is equal to negative 625 over 3 EI. Because it is negative, then point B is below. That's negative, below the reference tangent at C left. So the tangent is above B, as shown. Then this is deviation of B relative to the tangent at C left. So finally, we have form a right triangle here. And the slope at C left is obviously negative. It is sloping down to the right. So that's a negative slope, and it is opposite over adjacent. Tangent of theta, remember, is in beam deflection is simply opposite over adjacent. There's no need to say tangent of theta C left because it is expected small. Tangent of theta is just theta. So tangent of or theta C left is negative of absolute value deviation of B relative to C left plus delta C, absolute value of delta C divided by 5. So this is absolute value of deviation of B relative to C left, negative 625 over 3, plus this distance, which is equal to this delta C here, negative 5834.67 over EI divided by 5. So theta C left is negative 1208.6 over EI. So again, to keep me going, please share my lecture videos and sample problems to your friends and to your friends' friends.